Good morning, Prof. and fellow classmates. Today, our group will be presenting our topic, comparing machine learning models for inflation. I'm Yosheng, and my groupmates are Ziqi, Jonathan, Jason, and Kaisa. The contents of our presentation are as follows. I'll be starting off with the introduction. Inflation forecasting is one of the most important yet difficult undertakings in the sphere of economic forecasting, affecting businesses and households alike, while also being of utmost importance to central banks. Economic policy is heavily dependent on inflation rates, with most economic transactions happening in nominal terms. As such, the forecasting of inflation remains vital in the economic and policy-making sphere. The goal of our project is to consider a variety of machine learning methods and assess whether and to what extent they can forecast inflation rates with a focus on the UK economy. Our project will focus on the UK inflation rate with data taken from the UK macroeconomic database. Missing values are imputed using an expectation maximization algorithm and updated to our dataset. For our literature review, our key machine learning literature is the recent paper, Can Machine Learning Catch the COVID-19 Recession by Colomb and Marcelino, which entails in-depth machine learning forecasting frameworks and models that we can take inspiration from. This is supplemented by secondary sources such as Berkner's computational statistics and data analysis, which provides information on cross-validation and evaluation of time series predictions. Lastly, we refer to Chauvet and Potter's Handbook of Economic Forecasting for guidance on benchmarking models such as the AR and the MA models. As for our data, we obtained preliminary inflation data from the UK MD and check for correlation between covariates to prevent issues such as perfect multicollinearity. We then plotted out inflation to check for stationarity using a basic eyeball test as well as the Dickey-Fuller test. A ACF and PACF test was also completed, leading us to believe that the MA1 and AR3 models are suitable benchmark models. I will now pass on the time to Ziqi to discuss the next part.
Now, let's talk about the machine learning models we'll be using. We chose to consider a wide variety of machine learning models. We use both shrinkage models and regression trees, as well as hybrid models to combine the two. We also consider non-machine learning models as benchmarks to compare to. Firstly, we consider machine learning models using shrinkage, such as ridge regression, lasso, and the combined elastic net model. The shrinkage penalty will reduce overrepresentation caused by multicollinearity that we expect to see in macroeconomic data, which would tend to increase the variance of a linear model. The key distinctions between these models are that while our lasso models both shrinks and selects, our ridge regression model does not select variables for us. However, lasso may suffer from dropping key variables as a result of high covariance between variables, which is often seen in macroeconomic data, such as the ones we are using for this project. In order to negotiate between the pros and cons of both models, we also consider an elastic net model, which combines the two different models of penalty terms to obtain a more well-rounded estimate. In addition to shrinkage models, we also consider tree models to estimate and predict possible non-linear or non-parametric functions. The regression tree separates each dataset into regions to minimize the squared loss of each region, with the estimate of each being the simple mean. All three models seek to reduce the high variance of simple regression tree models in various ways. Bagging or bootstrap aggregating combines forecasts from different bootstrap samples in order to increase the number of samples in our data, reducing variance. Meanwhile, boosting seeks to aggregate models in a sequential fashion to increase predictability through slow learning. The random forest model selects random groups of predictors at each node, which decorrelates variables to reduce variance. In addition, we also consider hybrid models for our forecast, such as the random forest R-lasso hybrid. In the model, we first use the R-lasso model in order to perform variable selection, and then use the selected variables in the random forest model. This allows us to observe both variable selection while undertaking a non-linear model. The result of this hybrid method will also allow us to see if non-linearity or variable selection is more important in our model. In order to assess the effectiveness of each machine learning model, we must have some benchmarks to compare them to. We use the Box-Jenkins forecasting methodology to create models for both an autoregressive model and the moving average model, with the lag values decided by AIC values. In addition, we also consider a random walk model. This is because the random walk model is said to be the standard benchmark for inflation forecasting, and that traditional non-machine learning forecasting models do not provide significant improvements over the random walk model, which is said to be comparable to coin flipping its prediction. This is a quick summary of the characteristics of the models we have chosen. Now that we have discussed the machine learning models and their corresponding benchmarks, let us move on to our forecasting process.
Thanks, Ziqi. I'll now talk about our forecast procedure. Firstly, I'll explain our choice of machine learning model. The table shows the results of the mean square error of each model on our validation set. From these results, we chose the random forest model as it has the lowest mean square error, incorporating it into our time series data forecasting to compare with benchmark econometric models such as the random walk. Next, for our forecast procedure, we first set aside 85 observations from September 2014 to November 2021 for our pseudo out-of-sample analysis. Given the time series setting, differences in accuracy measures may not be significant enough to declare one model superior, as accuracy measures are merely sample estimates of population risk. Therefore, we instead opt to use the Debord-Mariano test to evaluate our forecasts against one another, which we will elaborate further on later in the presentation. I will now pass the time on to Jonathan.
Thank you, Kai-Xiang. So let's move on to the forecast horizon choice. We use H equal to 1, 3, 6, and 12 for H step ahead horizons corresponding to monthly, quarterly, half-yearly, and annually, respectively. These are the empirically relevant horizons that we choose given the stickiness of prices in the short run with respect to various macroeconomic predictors. We stop 12 months ahead as horizons beyond 12 months ahead results in multiple problems, especially given our machine learning setting. Computation costs increase exponentially since we are using a random forest. Larger forecast horizons usually are hard to assess for accuracy and face systemic bias. For the choice of estimation window, a fixed window includes only a fixed number of observations from the start of the sample to construct all the forecasts, which may potentially ignore newer data and is not desirable as we suspect model instability over time. For a recursive estimation window, it uses an additional observation for each subsequent forecast since the sample size increases for each subsequent forecast, which violates covariance stationarity. The rolling estimation window drops the first observation and includes a new observation at the end for each subsequent forecast. This estimation method ensures a fixed sample size and the use of most recent data, prevents contamination of forecasts with older irrelevant data, and guarantees covariance stationarity, which is a vital assumption for our use of the Debord-Mariano test. Thus, we decided to use a rolling estimation window. Now let's move on to Jason, who will discuss the forecast results.
Thank you, Jonathan. I will now carry on with the forecast results and evaluation. For the ER3 results, the one step ahead forecast explains more of the variations in the pseudo out sample than that of the 3-step ahead forecast. As the forecast horizon increases, the forecast explains increasingly less of the variations in the pseudo out sample. For random forest, one notable difference is that its one step ahead forecast explains more variation in the pseudo out sample compared to AR3 one step ahead forecast. What is similar between both forecast models is its weakening accuracy in explaining the variation in the pseudo out sample as the forecast horizon increases. To evaluate the forecast accuracy of the models, we employed the Debord-Mariano test. The Debord-Mariano test examines the loss differential between two competing models and verify if both losses from the models are equal. One important assumption of the test is the loss differential has to be covariance stationary, which we have already addressed the issue by employing rolling window scheme. We also use quadratic loss function to penalize negative and positive losses with the same magnitude. The loss differential equations are shown below. Here are the graphs for the loss differential for the competing models at different forecast horizons. It's very clear that covariance stationary is not violated as shown by the red dotted line, and thus suggesting that we are good to go for the Debord-Mariano test. We then use heteroscedasticity autocorrelation standard error to compute the standard errors for the loss differential equations, and then using a lag length that equals to the cube root of the pseudo out sample size, we arrive at the following results as shown in the table. The random forest model outperforms the random walk model at a 6-step ahead forecast and the AR3 model at a 1-step ahead forecast. This result shows that the random forest model does not definitively outperform econometric benchmark models at all forecast horizons, which may be due to small sample size problem or inappropriate loss function use. In summary, applying machine learning to time series forecasting is a novel concept that is not frequently explored in many literatures. Our team would expect machine learning models such as random forest to outperform econometric benchmark models a lot of the time, as random forest incorporates bootstrap aggregation to improve learners' abilities to produce forecasts. Yet, our paper does not show convincing results that the random forest is definitively better than econometric benchmark models at all forecast horizons. Perhaps it could be due to small pseudo-out sample size or inappropriate loss function use. Nonetheless, we have conclusive evidence that random forest can be at least on par with these benchmark models. Moving forward, we recommend to include forecast combination and other forecast evaluation methods such as MZ regression or HLN tests for a more holistic evaluation of the models. And with this, we have come to the end of our presentation. Thank you for listening to us.